Hey guys, we're going to take a look at a problem with an inclined plane where the box is going to slide down along the inclined plane. It's clearly not going to levitate above the earth or the table or the inclined plane, and it's not going to accelerate up the inclined plane because it would need some sort of net force to do that. So instead, we're going to just kind of place it right there where the center of mass is somewhere around here, and it is going to have the force of gravity acting down. The normal force is going to be perpendicular to the plane. And another thing that is something that we must establish right here and now, because it's important. The x direction is not going to be left and right. The y direction is not going to be up and down. Instead, we are going to change our perspective where we effectively will kind of tilt our head and look at it as if the x direction is the direction of the inclined plane, right? Because this box is going to slide and accelerate along this path, and it simplifies things if we make it so that way the object is accelerating at least in the direction of either the x or y plane. So with that in mind, that is going to be our x and y directionality. Let's go ahead and start looking at this problem a little bit more in detail. So what we have going on here is we have the force of gravity acting straight down, and I'm going to express that as mg, right? It is essentially ma, but g specifically because it is the acceleration of gravity. The normal force, again, that is going to be perpendicular to the plane. So if that is my little right angle, it is perpendicular to the plane. Do not forget that. I know that the size of these must be correct because when I do some basic vector addition and I go from the very beginning to the very end, let me kind of express that real quickly here. So from the very beginning to the very end, see how this arrow is parallel to the plane? This arrow, given that there's no other forces and it's possible that there's no friction here, that it's friction free, this arrow should demonstrate and show the direction that the box would slide. So it must be sliding along the plane, so that I must make these arrows in a direction and length so that way the resultant is along the plane. But I'm not terribly concerned about that at the moment. I'm just looking at the force of gravity at the moment. And so with the force of gravity, here's what I'd like to express. That, and in fact, what I'm going to do is I'm going to actually shift to my my nice arrow thing here, but specifically a dotted line. And so this is the kind of way I'd like you to do it. So I'd like you to make a dotted line where I'm going to draw the components of this force of gravity. The force of gravity, but I'm drawing the components of it. By the way, on the AP test, never draw the components of a force unless you are specifically told to. If it was a free body diagram, I would not be drawing the components. You must do that separately off to the side for your own purposes. So this is going to be the y component. This is effectively the vertical y component. And then the x component will look something like that. Let's see if I drew it correctly. If I were to grab this arrow, it should be parallel to the plane. And it's not quite exactly, so let me fix that. So that should be parallel to the plane, while the other one should be a length, so that way it's perpendicular to the plane, and it should be at a length something like that. So this should be a right angle. Now, if we have a situation where typically the angle of the inclined plane will be measured as this angle right here. So I could make up an angle, but I'm just going to express it as always. I'm just going to express it as theta. So I have this other triangle here. What other angle is also theta? Well, it is actually this angle in here. This angle is, in fact, theta. If you notice, I have a smaller triangle here. If this is a 90-degree angle and this is theta, this must be what I'll just call alpha. Okay, so that angle there is alpha. Well, this here is 90 degrees, okay? This angle here is 90 degrees. Let me erase that mark. And so if this here is 90 degrees, if this is alpha, then this must be theta, because alpha and theta together will always add 90. If this is 90, these two together will add 90. This must in fact be theta. If you ever get confused, just think about that. Otherwise, I think the easiest way to think about it is clearly one of these angles is the same. Within this triangle, one of these angles is the same. As the angle of the inclined plane increases, okay, as this theta increases, which one of these angles inside of this triangle would also increase? And so as the inclined plane increases, the normal, okay, must always stay perpendicular to the plane. And so with that, this angle would also increase. So that is another way to help you figure out which one of these angles is theta, if you can't remember. So these two angles are the same, and so with that, that means that this side of this triangle, okay, the hypotenuse of the triangle represents the force of gravity. This side of the triangle is going to be the force of gravity in the y direction. And so I'm going to express that, right? This is the force of gravity in the y direction. And since this is angle theta, right, the hypotenuse is equal to mg, since this is theta, this is the adjacent side of the triangle. So that means that this is equal to cosine of the angle theta times mg. And then this side of the triangle here, this is going to be the force of gravity in the x direction. And since it's the opposite side of the triangle, this is going to be sine. So this is equal to the sine of angle theta, and put that in parentheses, times mg. Okay, so we have cosine of theta times mg, the sine of theta times mg. Okay, so now what I'm going to do is I'm going to break this down, and I can go ahead and switch colors. I'm just going to make it a light color. Sure, why not? I'm going to say that stating Newton's second law, I'm going to state that we have to make Newton's second law twice. Once for the vertical direction and once for the horizontal direction, right? Vertical being this way, horizontal being this way. So let me say that the sum of all forces in the y direction is equal to ma, which is in turn equal to any positive forces plus or minus any, other forces. So I'm going to say that this direction here is a positive direction. So I'm going to say that it is going to be equal to the normal force plus or minus any other forces that are acting on it. And since this box clearly is not levitating above the inclined plane, there must be some sort of equal and opposite force acting on it, and that would be the force of gravity in the y direction. So I'm going to say minus the force of gravity in the y direction. And again, since it's not accelerating in this direction whatsoever, I'm going to say this whole thing, right, acceleration is equal to 0, which means that the whole thing is equal to 0. That means in turn, right, that's my arrow, that means that in turn that the normal force is equal to the force of gravity in the y direction. And of course, as we had expressed, the force of gravity in the y direction is equal to the cosine of the angle theta. See if I can make this fairly neat, times mg. I wouldn't really call that neat, but I think that you know what I'm going for there. And there, I'm done for the y direction. And it is important on the EP test to express things like this. It might be obvious that these are two things are equal and opposite, but they typically will want you to express this so that we can demonstrate why. That right there might be part of the rubric. So let's look at the x direction. So the sum of all forces in the x direction, again, is equal to ma. And I think that something that I had meant to express, but I didn't, and I'll go back and do that now, is that if this is the sum of all forces in the y direction, then the ma must be equal to the ma in the y direction. This here is the x direction, so it must be the acceleration in the x direction, okay? This is the acceleration in the x direction. That is ugly as sin, so I must change that. But this is the x direction. marginally better, which in turn is equal to all the forces added up acting in that direction. Remember that the x and y components can be completely independent of each other. So what do we have acting in a positive direction? Well, since the object can accelerate only in this down and to the right direction, I'm going to make that positive. Doesn't really matter, it's arbitrary, but it just makes things a little bit simpler. So since that's the x direction, I'm going to say that this is a positive force. So I'm just going to start off simply. I'm going to say that this is the force of gravity in the x direction, plus or minus any other forces. Well, what else do we have? Well, let's go ahead and throw this in. So we also have another force, and I'm going to say that friction is in fact acting on it. That friction is acting in a direction that is up the plane. Now, depending on the size of that friction, it could only be as large as the force of gravity, right? In this case, this means that the object is not accelerating down the plane. Is it moving? Well, that remains to be seen. It could be having already been set in motion, and it is now just constantly moving down the plane with a constant velocity. Or it could be static friction, right? Instead of kinetic and sliding, it could be static friction and not sliding. So this box is just not sliding down the inclined plane, and friction is enough to hold it back. If it is sliding and accelerating, then this force must be smaller. So not only is it sliding, but it is accelerating down the inclined plane. So let's, for the moment, assume that this force is perhaps equal to, or maybe even smaller, but friction is in fact there. We're going to go through both scenarios here. The case where it's smaller or the case where it's equal to. Okay, so we do have friction. So I'm going to say that friction is acting in a negative direction. So minus the force of friction. And my tablet skills are running a little bit subpar today, so excuse me on that. What I'm going to do is I'm going to now substitute the things that I know about the x direction, force of gravity, and also the force of friction. So if you don't already know, at all times the force of friction is equal to mu k, which is the coefficient of kinetic friction, times the normal force. You could say also that the force of friction is less than or equal to mu s times the normal force. What this means is that this would be that scenario where the force of friction is equal to the gravitational force that is trying to push it down the inclined plane, so it's not moving anywhere, it's not accelerating. And so if you have, as you increase the force acting on something, the force of friction will also increase and, to correspond until the moment it breaks free of friction. What I'm going to be concerned about is either two scenarios. Either the moment that it breaks free from friction, right, when the inclined plane becomes such a great angle to where it just can't hold back anymore and the box starts to slide, or the scenario where it is in fact sliding and accelerating. So let's look at those scenarios. And in that case, I'm not concerned about the part where it's less than. I'm only concerned about the part where it's equal to. Okay, so I'm going to treat it like it's just equal. That would be the point at which you have an inclined plane and the box just kind of starts to slide at that moment. All right, so I'm going to go ahead and do these substitutions. So I'm going to say that ma in the x is equal to, let's see here, in the x direction we're looking at sine, that would be this part here. So the force of gravity in the x direction is equal to the sine of angle theta times mg minus, well, let's just say that it's static friction, and I'll get into that. So it's going to be mu s times the normal force. Okay, but wait, what do we know about the normal force? The normal force is equal to the force of gravity in the y direction, which is in turn also equal to cosine theta mg. So let me rewrite this. So max ma in the x is equal to sine of angle theta times mg minus mu s times, as I said, cosine theta times mg. Okay, so right here, there's something we can take from this. First off, what if I just wanted to find the acceleration of the box down the plane? You should recognize that since these two equations are virtually the same, instead of this being mu s, it could be mu k, and it is in fact accelerating. It would be the same equation. So if acceleration did in fact have a value, that could be mu k, and m would cancel across the board, right? So this m cancels with that one and that one. So your acceleration down the plane would be equal to sine theta g minus mu k cosine theta g. The m cancels. Okay, so that would be the acceleration down the plane, and that could be a question on the AP test. Find the acceleration of the box down the plane in these variables. Boom, that would be your answer. This would be mu k, and the m's would be canceled. Okay, and I can write that a little bit later. But let's again express this as mu s, where it's not accelerating. Okay, fine. So the acceleration is equal to 0. Okay, because this is mu s, it is static friction, and it is not accelerating down the plane. Well, if that's true, then this whole thing kind of goes away, and we need to set this whole thing to equal to 0. So I'm going to add each side by mu s cosine theta mg. So sine theta mg equals mu s cosine theta mg. And what you should notice is that, again, the m's cancel. Okay? And if I divide each side by cosine theta g, that means that mu s is equal to sine theta. Oh, wait, the g's also cancel, don't they? Okay, so it's sine theta over cosine theta. What's that equal to? Tangent theta. Okay, so let's kind of take a look at that. Yeah, so let's look at what this means. This means that if you have an inclined plane and a box, as you increase the angle of the inclined plane, eventually you will get to an angle to where you will have, oh, and there it is. You will get to a point where the angle is so large that the applied force along the plane, which is the force of gravity along the plane, right, this in this direction, the force acting in that direction will be larger than the force of friction acting that way. And at that moment, we'll be at a point to where the coefficient of static friction is, it's breaking free. And so this is actually a way to figure out what the coefficient of static friction is, okay? In fact, let's see if I can kind of express this a little bit differently. So here's what's another way that we can solve for the coefficient of static friction. So if I just have a box on a flat surface, I could pull on that box horizontally with some sort of string. And so this would be my applied force. And then acting on that box would be a friction force acting in the opposite direction. So as I pull on the box just a tiny bit, but it's not moving yet, and then I pull a little harder, a little harder, a little harder, and eventually it breaks free and it starts to slide. So it's harder, 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 and it starts to break free. And when it breaks free of that static friction, okay, the force of friction, or in fact, let me just express it this way, the coefficient of static friction at that point will be equal to the force of friction divided by the normal force. Well, the normal force on a flat surface is going to be mg. So it's going to be the friction force divided by mg, and that will be the coefficient of static friction. Keep in mind that with like a car, wheels, the friction between the tire and the road is typically going to be static friction as long as it's not sliding. It's a different point of contact with the road at each moment in time. So if you have a coefficient that is equal to 1, that means that the friction force causing the car to accelerate is as large as mg. That means that you are pulling, if you are in a car and you're turning and you have a coefficient of 1, that means you're going to pull 1g that way. In Formula 1, race cars can pull 6 Gs. Crazy. Okay? So that's one way of determining the coefficient, is you can figure out what the friction force is, right? The friction force is going to be equal to the applied force at the point where it breaks free. And so take that divided by mg. And that's a pretty easy way to calculate it. But another even easier way to calculate it would be to take this object and put it on an inclined plane like what we have shown, and you just raise the angle until it breaks free, okay? And if you measure that angle with the horizontal, okay, if you measure that angle relative to the horizontal, tangent of that theta, of that angle, that'll give you the same value, gives you the same answer as the experiment that we just described. Okay, so that is one way to solve for the coefficient of static friction. Now let's look at an object in which there is actually an acceleration. Okay, so let's take a look at this. So what if we back up? Okay, I'm going to actually just go ahead and start backing up and doing some erasing here. All right, so now I want to treat it as though we have, instead of static friction, I'm going to say it's kinetic friction. That's a terrible, terrible thing. I'm just going to erase this part. Okay, I'll just rewrite it. That's fine. And so we have mu k times cosine theta mg. And of course, this is no longer equal to 0 because the object is in fact accelerating down the plane. So with your notes at home, I would suggest that you kind of rewrite this part for another scenario. In the previous scenario, it was if acceleration is equal to 0, then those things would be true. Now we are rewriting this part, and in this case, this would be if acceleration is larger than 0. So I would note that, pause it if you need to, and note that in your notes, okay? So now we have a situation where the acceleration is in fact larger than 0. And so as I said, m would cancel across the board. If you don't recognize why m would cancel, factor the m out, okay? Then you would see that it cancels, okay? You would have m factored out on the right, and it would in fact cancel. So I've gone ahead, I didn't want to waste my time. Excuse me, I don't want to waste your time just watching me, but I went ahead and drew that out so that you can see that the m's in fact do cancel. It's a little bit easier to notice. So the acceleration is equal to all this stuff inside the parentheses. Forgot my final parenthesis there. And so you can just, that could be a solution to a problem where you're trying to find the acceleration. Or what if an object is accelerating, yet you still want to find the coefficient of friction? Okay, let's just rearrange this to solve for the coefficient of friction. I can add each side by mu k cosine theta g and subtract each side by a. So that means that mu k cosine theta g is equal to sine theta g minus a. And then divide each side by cosine theta g. So that means that mu k is equal to sine theta g minus a all over cosine theta g. And that would give you the acceleration, excuse me, that would give you the coefficient of kinetic friction. That's a k. That's a k. And so what if you had, let's say you went sledding, right, down an inclined plane, which is usually what you do, right? You go sledding down a hill. You could measure the acceleration, right? You have the beginning point and the end point. You can measure the amount of time it takes for you to go between the 2 points, and you can use a simple kinematic equation to figure out the acceleration along that distance. Once you have that acceleration, g is 9.8, you could figure out what the angle of the slope is. That's actually fairly simple to do as well. You could bring some sort of surface, some sort of flat surface onto the hill, and you can just kind of like tie a string of some kind, grab some headphones, and you can just kind of have an object just kind of dangle. And if you have a protractor, you can figure out what the angle is. Okay? And guess what? That's a lab that I do pretty much every year. I do that with students where we go sledding, we measure the angle, do the sledding, and actually figure out what the coefficient of friction is between the sled and the snow. The difficult part is that coefficient does change as you ride through the hill and the snow gets packed down, but fun lab nonetheless. But yeah, hopefully that's something that we can do. Maybe at home, have you guys kind of do that. We'll see. But hopefully you guys learned something. And remember, whenever you solve these problems, there's a couple things to watch out for. For one, that you kind of have to tilt your head to look at the problem, so that way along the plane is the x direction. The other thing to watch out for is super common mistake is, let me switch something. Okay, so super common mistake is to draw this incorrectly. I see this happen all the time, where this is drawn in this sort of direction, and we cannot do that. This component must be parallel to the inclined plane. Okay, this must be parallel to the inclined plane. Sometimes I'll even see somebody draw, I don't know what sometimes happens, but that's probably the most common mistake. This must be parallel, okay, this must be parallel to the inclined plane, and this one must end right there. So we should have a right angle here. That's definitely the most common mistake. Keep in mind also that we have to write Newton's second law twice. Once for the vertical component, the vertical being, sort of tilted, and the horizontal, again, the horizontal being sort of tilted in this case. So they are totally independent of each other. And then lastly, I think that is the last thing I want to reiterate, is do not draw components when you're drawing a free body diagram for the AP test. If they are asking you to draw the components, or excuse me, if they're asking you to draw the forces acting on an object, you draw only the forces acting on the object. So in this case, we would just say, okay, well, that's our object, that's the box. What are the forces acting on the box? We have mg acting down, and we have the normal force acting up and at an angle, and we also have the force of friction acting in that direction. This would be the free body diagram. I would probably get 3 points for each arrow, and if you were to draw the components, you would get -1 point there, and you would get -1 point there. They will deduct points for each erroneous force drawn. So do not draw the components unless they specifically ask for it. That's what I got. Sorry if it's too long, but there's a lot there, and it is very useful. So you guys let me know if you have any questions, and I'll see you next time.